Welcome to Astro Odyssey. Explore the universe. Imagine a star so powerful that if it appeared anywhere near our solar system, it could destroy life on Earth without even touching the planet. A star so extreme that its magnetic field could twist atoms, disrupt technology across an entire world, and release more energy in a fraction of a second than our sun produces in hundreds of thousands of years. This object is not science fiction. It is not a theoretical idea created by scientists for movies or novels. It is real, and astronomers have already discovered several of them scattered across our galaxy. These extraordinary objects are called Magnetars, and they are among the most dangerous and mysterious objects ever discovered in the universe. To understand why Magnetars are so terrifying, we must first understand just how strange and extreme the universe can be. Space is not a calm or peaceful place. It is filled with violent forces and unimaginable energy. Entire galaxies collide with each other over billions of years. Black holes consume stars and gas clouds with unstoppable gravity. Supernova explosions can briefly outshine entire galaxies, releasing enormous amounts of radiation into surrounding space. Yet even in this violent cosmic environment, Magnetars stand out as something uniquely powerful and bizarre. They are stars that push the limits of physics itself. A magnetar is a special type of neutron star, and neutron stars are already among the strangest objects known to science. When a massive star reaches the end of its life, it can collapse under its own gravity in a catastrophic explosion known as a supernova. The outer layers of the star are blasted into space, creating enormous clouds of glowing gas and dust. What remains behind is the collapsed core of the original star, compressed into an object incredibly small, yet unbelievably dense. This remnant is what scientists call a neutron star. Neutron stars are difficult to imagine because their properties are so extreme. They contain roughly the same mass as our sun, but instead of being spread across a sphere more than 1,000,000 kilometers wide, that mass is squeezed into an object only about 20 kilometers in diameter. In other words, something with the mass of an entire star is compressed into something roughly the size of a city. The result is an object with density so extreme that a single teaspoon of neutron star material would weigh billions of tons if it were brought to Earth. But magnetars go far beyond even this level of extremity. While all neutron stars are dense and powerful, magnetars possess an additional feature that makes them truly extraordinary: their magnetic fields. The magnetic field of a magnetar is the strongest magnetic field ever observed in the universe. It is trillions of times stronger than the magnetic field surrounding Earth. In fact, the magnetic force generated by a magnetar is so powerful that it can affect matter and energy across enormous distances in space. To understand how strong this magnetic field really is, imagine placing a magnetar somewhere within our solar system, even if it were located hundreds of thousands of kilometers away from Earth. Its magnetic field could still interfere with electronic devices across the planet. Credit cards, computer hard drives, and communication systems could all be wiped out instantly. Satellites orbiting Earth would begin malfunctioning almost immediately. Navigation systems, such as GPS, would collapse. Power grids across the planet would experience catastrophic failures. In a world that relies heavily on technology, the sudden loss of these systems would cause immediate global chaos. But the effects of a magnetar would not stop with technology. The magnetic field surrounding such an object is so intense that it can begin to distort the very structure of matter itself. Atoms, which normally have a stable and predictable shape, become stretched and deformed under the influence of this extreme magnetism. The electrons orbiting atomic nuclei could be pulled into unusual configurations, altering the behavior of molecules in chemical reactions. Matter itself would begin to behave differently. Even light can be affected by a magnetar's magnetic field. Normally, light travels through space in straight lines unless it encounters gravity strong enough to bend its path. This phenomenon is known as gravitational lensing, and it is commonly observed around massive objects like black holes and galaxies. But magnetars introduce an entirely different type of distortion. Their magnetic fields are so powerful that they can actually influence the way light travels through empty space. Photons moving near a magnetar can be twisted or split into different polarization states, creating strange optical effects that challenge our understanding of physics. Scientists sometimes describe the region around a magnetar as a place where the vacuum of space itself behaves differently. In ordinary conditions, empty space allows light to travel freely without interference. Near a magnetar, however, the intense magnetic field alters the properties of space itself, creating an environment where even fundamental physical processes can change. Despite their incredible power, magnetars are relatively small objects. Compared to ordinary stars, they are tiny. A magnetar's diameter is typically only about 20 kilometers, which is smaller than many cities on Earth. Yet within that small volume lies a tremendous amount of energy. The combination of extreme density and powerful magnetism makes magnetars one of the most compact and energetic objects in the universe. Astronomers believe that magnetars are relatively rare. Our galaxy, the Milky Way, contains hundreds of billions of stars. Yet scientists have identified only a few dozen magnetars so far. These objects are usually located thousands or even tens of thousands of light years away from Earth, which means they pose no immediate threat to our planet. However, their existence reminds us of how extreme the universe can be. Even from across the galaxy, magnetars have demonstrated their power. In 2004, astronomers detected an enormous burst of energy coming from a magnetar located about 50,000 light years away. The burst lasted less than half a second, yet during that brief moment, it released more energy than our sun produces in 100,000 years. Instruments on satellites detected the radiation even from that enormous distance. For a brief moment, Earth's atmosphere itself reacted to the incoming energy. Events like this reveal just how powerful magnetars truly are. They are not simply unusual stars. They are cosmic engines capable of releasing staggering amounts of energy in incredibly short periods of time. They represent one of the most extreme outcomes of stellar evolution, where gravity, nuclear physics, and magnetism combine to create something unlike anything we experience on Earth. And yet magnetars do not exist forever. Like all cosmic objects, they evolve and eventually fade. Their magnetic fields slowly weaken over thousands of years, and the violent bursts of radiation they produce gradually become less frequent. Eventually, a magnetar may transform into a quieter neutron star, still dense and powerful, but no longer the magnetic monster it once was. But during the short period when a magnetar is active, it becomes one of the most powerful objects in existence. It can shake space with bursts of energy, distort matter with its magnetic forces, send signals across vast distances in the universe. And somewhere out there, hidden among the billions of stars in our galaxy, these incredible objects continue to spin silently in the darkness, waiting for the moment when their immense magnetic energy erupts once again. To truly understand how magnetars are born, we must travel back to the life of a massive star, long before the magnetar itself ever exists. Every magnetar begins as something much larger, much brighter, and much more familiar, a giant star burning in the depths of space. Stars are not static objects. They are constantly evolving, changing over millions or billions of years as nuclear reactions inside their cores transform simple elements into heavier ones. At the center of every star lies a delicate balance between two enormous forces. Gravity is constantly pulling the star inward, trying to collapse it into a smaller and denser object. At the same time, nuclear fusion deep inside the star's core releases vast amounts of energy. producing pressure that pushes outward against gravity. As long as these two forces remain balanced, the star remains stable. For stars like our Sun, this balance can last for billions of years. The Sun has been shining for about 4.5 billion years, and it will continue shining for several billion more before it begins to change dramatically. But massive stars live very different lives. The more massive a star is, the faster it burns through its nuclear fuel. Some stars, dozens of times heavier than the Sun, may live for only a few million years before reaching the end of their lives. Inside these massive stars, nuclear fusion occurs at an incredible pace. Hydrogen atoms fuse together to form helium, releasing enormous amounts of energy. As the star ages and hydrogen becomes scarce, the core begins fusing helium into heavier elements such as carbon and oxygen. Eventually, even heavier elements begin forming through a chain of nuclear reactions that grow more and more extreme. The core of the star becomes like a cosmic factory, forging new elements under tremendous pressure and temperature. Carbon becomes neon. Neon becomes oxygen. Oxygen becomes silicon. Each stage burns faster than the one before it. What took millions of years earlier in the star's life may now take only thousands or even days. Eventually, the process reaches iron. Iron is different from other elements created inside stars. When lighter elements fuse together, they release energy that helps support the star against gravity, but iron does not release energy when it fuses. Instead, it absorbs energy. When a massive star's core becomes mostly iron, the delicate balance that kept the star stable for millions of years suddenly collapses without the outward pressure from nuclear fusion. Gravity takes control. The core of the star begins collapsing inward at incredible speeds. In just a fraction of a second, the core shrinks dramatically, compressing matter to densities that are almost impossible to imagine. Electrons and protons inside atoms are crushed together under the enormous pressure, forming neutrons and releasing floods of tiny particles known as neutrinos. As the core collapses, the outer layers of the star suddenly lose their support. They begin falling inward toward the collapsing core at thousands of kilometers per second. For a brief moment, the entire star seems to implode. Then something extraordinary happens. When the collapsing core reaches an incredibly dense state, it suddenly becomes almost incompressible. The matter inside is packed so tightly that it cannot collapse much further. The inward rush of material from the outer layers slams into this dense core and rebounds outward violently. The result is one of the most powerful explosions in the universe, a supernova. During a supernova, the outer layers of the star are blasted into space at incredible speeds. Shock waves travel through the surrounding gas and dust, creating enormous expanding clouds known as supernova remnants. For a short period of time, the exploding star can shine brighter than billions of other stars combined. If such an explosion occurred near Earth, it would be visible even during the daytime sky. Ancient civilizations occasionally recorded these events as mysterious guest stars, appearing suddenly in the heavens. But while the outer layers of the star explode outward, the core remains behind. This core is no longer an ordinary star. It has been crushed by gravity into something far stranger. In many cases, the core becomes a neutron star. Neutron stars are among the densest objects in the universe. The matter inside them is packed together so tightly that the normal structure of atoms no longer exists. Instead of electrons orbiting atomic nuclei, the particles have merged into a sea of neutrons pressed together by immense gravity. This creates an object only about 20 kilometers wide, yet containing more mass than the Sun. To put this into perspective, imagine compressing Mount Everest into something the size of a grain of sand. That would still not approach the density of a neutron star. But under certain conditions, something even more extraordinary can occur. If the newborn neutron star is spinning extremely fast and possesses enormous magnetic energy, its magnetic field can become amplified to incredible levels during the collapse. As the star shrinks, its magnetic field lines are squeezed closer together, dramatically increasing the strength of the field. This process is somewhat similar to what happens when a figure skater pulls in their arms while spinning. As their arms move closer to their body, their rotation speeds up dramatically. In a collapsing star, the shrinking core can cause both the rotation and the magnetic field to intensify. In rare cases, this amplification becomes extreme. The newborn neutron star emerges with a magnetic field trillions of times stronger than Earth's. At that moment, a magnetar is born. This transformation occurs incredibly quickly. Within seconds of the supernova explosion, core settles into its new state as one of the most extreme objects in existence. The magnetar begins spinning rapidly, sometimes completing several rotations every second. With each rotation, its enormous magnetic field twists and interacts with the surrounding space, storing tremendous amounts of energy. This energy does not remain trapped forever. Over time, the magnetic field begins to shift and rearrange itself. When this happens, enormous bursts of energy can erupt from the magnetar's surface, sending powerful waves of radiation across the galaxy. These eruptions are among the most violent events that can occur without destroying the star itself. And this is what makes Magnetar so fascinating to scientists. They represent a stage in stellar evolution where the laws of physics are pushed to their limits. Gravity, nuclear forces, magnetism, all interact in ways that create extraordinary phenomena. Yet magnetars are not simply cosmic curiosities. They may also play an important role in shaping the universe around them. The material blasted into space by the original supernova explosion contains heavy elements that later become part of new stars, planets, and possibly even life itself. Iron in our blood, calcium in our bones, and oxygen in the air all originated in ancient stellar explosions billions of years ago. In that sense, the violent death of massive stars is also the beginning of something new. But while supernova explosions create the raw materials for future worlds, the magnetar left behind continues to evolve in its own dramatic way. Its powerful magnetic field begins interacting with space itself, and over time, that magnetic energy will unleash some of the most intense bursts of radiation ever observed in the cosmos. The birth of a magnetar may last only a few seconds, but the consequences of its existence can echo across the galaxy for thousands of years. When the violent explosion of a supernova finally fades, what remains at the center of the expanding debris is one of the strangest objects in the entire universe. The collapsed core of the massive star no longer resembles an ordinary star at all. It has become something far smaller, far denser, and far more extreme. This remnant is known as a neutron star, and understanding what exists inside it pushes the limits of modern physics. A neutron star may appear tiny compared to normal stars. While the sun is more than 1 million kilometers across, a neutron star is typically only about 20 kilometers in diameter. That is roughly the size of a large city. Yet inside this incredibly small object lies more mass than our sun contains. The amount of matter packed into such a small volume creates densities that are almost impossible to imagine. To grasp just how dense a neutron star really is, scientists often use a simple comparison. If you could somehow scoop up a teaspoon of neutron star material and bring it to Earth, that tiny amount of matter would weigh around 1 billion tons. That is roughly equal to the weight of Mount Everest compressed into something small enough to fit on a spoon. Of course, such a scenario is impossible. Neutron star material cannot exist under the normal conditions found on Earth. the moment it left the intense gravity of the neutron star, it would violently explode back into ordinary atoms. But imagining that tiny teaspoon helps illustrate just how extreme these objects truly are. The reason neutron stars are so dense lies in the incredible forces that exist inside them. During the collapse of a massive star, gravity becomes so powerful that the normal structure of atoms is completely destroyed. Under ordinary conditions, atoms consist of a nucleus surrounded by a cloud of electrons. The nucleus itself contains protons and neutrons, bound together by the strong nuclear force. But inside a collapsing stellar core, gravity becomes so intense that electrons are forced into the nuclei of atoms. When electrons combine with protons, they form neutrons. As this process spreads throughout the collapsing core, the matter inside becomes dominated by neutrons packed tightly together. The result is a gigantic sphere made mostly of neutrons, compressed together in a state of matter unlike anything found on Earth. In many ways, a neutron star can be thought of as a single enormous atomic nucleus, roughly the size of a city. The gravity on the surface of a neutron star is equally astonishing. Because so much mass is packed into such a small space, the gravitational pull near the surface becomes incredibly strong. If a person somehow managed to stand on a neutron star, their body would experience a gravitational force billions of times stronger than what we feel on Earth. Of course, no human could survive such conditions. Even the strongest materials known to science would be crushed instantly under that immense pressure. But neutron stars are not just dense and heavy, they are also incredibly fast. When a massive star collapses, the conservation of angular momentum causes the resulting neutron star to spin rapidly. This is similar to what happens when a figure skater pulls their arms close to their body during a spin. As their arms move inward, their rotation speed increases dramatically. The same effect occurs when a star shrinks from a massive sphere, thousands of kilometers wide, into a compact object only 20 kilometers across. The result is an object spinning at incredible speeds. Some neutron stars rotate several hundred times per second. These rapidly spinning neutron stars are known as pulsars because they emit beams of radiation that sweep across space like the rotating beam of a lighthouse. Each time the beam crosses Earth, astronomers detect a pulse of radio waves or other radiation. But which are a special type of neutron star, behave differently from ordinary pulsars. While pulsars are known mainly for their rapid rotation and regular pulses of radiation, magnetars are dominated by their enormous magnetic fields. These magnetic fields are so powerful that they store vast amounts of energy within and around the star. Over time, that energy can be released suddenly in dramatic bursts of radiation. To understand why Magnetars develop such powerful magnetic fields, scientists believe the key lies in the early moments after the neutron star is formed. When the collapsing core begins spinning extremely rapidly, the motion of electrically charged particles inside the star can generate powerful magnetic fields. Through a process known as the dynamo effect, this process is somewhat similar to how Earth generates its own magnetic field. Deep within our planet's core, the movement of molten metal creates electric currents that produce a magnetic field surrounding the planet. But the conditions inside a newborn neutron star are far more extreme. The rotation speeds are much higher, and the densities are vastly greater. As a result, the magnetic field generated during this process can reach extraordinary strengths. In some cases, the field becomes trillions of times stronger than Earth's magnetic field. When this happens, the neutron star becomes a magnetar. Inside a magnetar, the intense magnetic field places enormous stress on the star's crust. Although neutron stars are incredibly dense, they still possess a thin outer crust made of tightly packed atomic nuclei. This crust behaves somewhat like a solid shell surrounding the interior of the star. But the magnetic forces inside a magnetar constantly twist and pull at this crust. Over time, the stress builds until the crust suddenly cracks. When this happens, enormous amounts of magnetic energy are released in the form of high-energy radiation. These events are known as starquakes, and they can produce some of the most powerful bursts of energy ever observed in the universe. Scientists have detected these bursts using space-based observatories that monitor gamma rays and X-rays. Some magnetar flares release more energy in a fraction of a second than our sun produces over thousands of years. Even when these events occur on the other side of the galaxy, their radiation can still be detected by instruments orbiting Earth. Despite their incredible power, neutron stars and magnetars are difficult to observe directly. Because they are so small and distant, they often appear only as faint points of light in telescopes. Most of what scientists know about them comes from studying the radiation they emit and analyzing how that radiation changes over time. Yet even with limited observations, neutron stars have become one of the most important laboratories for studying the laws of physics under extreme conditions. The matter inside them exists at densities and pressures far beyond anything we can recreate on Earth. By studying neutron stars, scientists hope to better understand how matter behaves when compressed to the limits allowed by nature. These extraordinary objects also remind us of something profound about the universe. The same physical laws that govern atoms and particles on Earth also shape the behavior of the most extreme objects in space. From the smallest particles to the densest stars, the universe is connected by the same fundamental principles, and yet neutron stars remain mysterious. There are still many unanswered questions about their interiors, their magnetic fields, and the strange forms of matter that may exist deep within their cores. But one thing is certain. When a neutron star possesses a magnetic field, powerful enough to dominate its behavior, it becomes something even more extraordinary. It becomes a magnetar. In the universe, many objects possess magnetic fields. Planets, stars, and even entire galaxies generate magnetism through the movement of charged particles. On Earth, our planet's magnetic field is produced by the motion of molten iron deep within the outer core. This invisible shield surrounds our planet and protects life from dangerous solar radiation streaming from the sun. Without it, Earth's atmosphere would slowly erode, and the surface would become far more hostile to life. But Earth's magnetic field is gentle compared to the magnetic forces that exist elsewhere in the universe, even the sun, which is far more powerful than Earth in many ways, has a magnetic field that is relatively moderate on cosmic scales. The sun's magnetic field shapes solar flares, sunspots, and powerful eruptions known as coronal mass ejections. These events can send bursts of charged particles across the solar system and occasionally disrupt satellites and power grids on Earth. Yet, the sun's magnetism is insignificant when compared to the magnetic field of a magnetar. Magnetars possess the strongest magnetic fields ever observed in the known universe. Their magnetic strength is so extreme that it challenges the limits of what physics allows. Scientists estimate that a typical magnetar's magnetic field may be around 1 quadrillion times stronger than Earth's magnetic field. To understand what that means, imagine the strongest magnets ever created by humans. Even the most powerful laboratory magnets produce fields that are only a tiny fraction of what exists around a magnetar. The difference is so vast that comparing them is almost meaningless. The magnetic field surrounding a magnetar is so powerful that it can affect objects from enormous distances. If a magnetar were located halfway between Earth and the Moon, its magnetic influence would still be strong enough to disrupt electronics across our planet. Hard drives would fail. Credit cards would be erased instantly. Satellites orbiting Earth could stop functioning, but technology would be the least of our concerns. At closer distances, the magnetic forces surrounding a magnetar begin interacting directly with matter itself. Atoms, which normally maintain stable shapes, governed by the balance between electrons and nuclei, would begin to behave differently in such intense magnetic environments. Under normal conditions, electrons orbit atomic nuclei in roughly spherical clouds. These clouds define the shape of atoms and influence how atoms bond together to form molecules. But in the presence of an extremely powerful magnetic field, those electron clouds can become stretched and distorted. Near a magnetar, atoms may become elongated into strange shapes, almost like tiny needles aligned with the magnetic field lines. Chemical reactions that normally behave predictably could begin acting in unfamiliar ways. In other words, the rules of chemistry themselves could change. The magnetic field surrounding a magnetar also stores enormous amounts of energy. Over time, that energy can become unstable. As the field twists and shifts around the star, tension builds within the magnetar's crust. When this tension becomes too great, the crust can crack violently. These cracks trigger enormous bursts of radiation, known as magnetar flares. During a magnetar flare, the star releases a sudden explosion of energy that travels through space in the form of gamma rays and X-rays. These forms of radiation carry extremely high energy and can travel vast distances across the galaxy. Some of these flares are so powerful that they can briefly outshine every other source of gamma radiation in the sky. One of the most dramatic examples occurred in December of 2004. Astronomers detected an enormous burst of gamma radiation coming from a magnetar located roughly 50,000 light-years away from Earth. The event lasted less than half a second. Yet during that brief moment, the magnetar released more energy than our sun produces in about 100,000 years, even from that incredible distance. The radiation was strong enough to affect Earth's atmosphere. Instruments on satellites recorded a sudden spike in gamma radiation, and the upper layers of Earth's atmosphere reacted to the incoming energy. If the same event had occurred much closer to Earth, the consequences could have been devastating, but magnetars influence more than just matter and radiation. Their magnetic fields can also affect light itself. Normally, light travels through empty space without being influenced by magnetic fields. Gravity can bend light, as seen around massive objects like black holes and galaxies. But magnetars introduce something even stranger: the extreme magnetic field surrounding. A magnetar can change the way light behaves in a vacuum. In physics, empty space is often thought of as a simple background through which light travels freely. But near a magnetar, the magnetic field becomes so strong that it alters the properties of the vacuum itself. This phenomenon is known as vacuum birefringence. In simple terms, the intense magnetic field causes space to behave like a kind of optical crystal. Light passing through the region around the magnetar can split into different polarization states, causing strange distortions in the light that reaches distant observers. This effect is incredibly subtle and difficult to detect, but scientists have gathered evidence suggesting that it may occur near magnetars. If you could somehow observe the sky from a safe distance near the stars behind it might appear distorted or twisted due to the interaction between light and the magnetic field. Of course, no spacecraft or human observer could survive anywhere close to such an object. The radiation and magnetic forces would destroy any known material long before reaching the surface. Despite these dangers, magnetars continue to fascinate astronomers because they offer a unique opportunity to study physics under conditions that cannot be recreated on Earth. Laboratories. on our planet can produce powerful magnetic fields, but they last only for brief moments and are far weaker than those found around magnetars. By observing these distant objects, scientists gain insight into how matter, radiation, and magnetic forces behave under extreme conditions. Magnetars also help scientists understand how energy moves through the universe. Their flares and bursts can travel across enormous distances, providing clues about the structure of space and the distribution of matter in our galaxy. Even though they are rare, magnetars represent one of the most extreme outcomes of stellar evolution. They are the result of gravity compressing matter beyond ordinary limits, rotation amplifying magnetic forces to extraordinary levels, and physics combining in ways that create objects unlike anything else in the universe. And yet, for all their power, magnetars are not eternal. Their magnetic fields slowly weaken over time. As the energy stored within those fields dissipates, the violent flares and bursts become less frequent. The star gradually settles into a quieter state. Eventually, the magnetar may become an ordinary neutron star, still dense and powerful, but no longer capable of producing the same dramatic magnetic phenomena. But during the brief period when its magnetic field remains strong, a magnetar becomes one of the most powerful objects in the cosmos, a small star with the power to distort atoms, bend light, and release energy capable of shaking an entire galaxy. And if such an object ever appeared close to Earth, the effects would be unlike anything humanity has ever experienced. Throughout human history, our planet has faced many cosmic dangers. Asteroids have collided with Earth and caused mass extinctions. Comets have passed dangerously close to our orbit. Even powerful solar storms from our own sun occasionally disrupt satellites and electrical systems across the globe. Yet compared to many phenomena in the universe, these events are relatively mild. Now, imagine something far more extreme. Imagine that somewhere in our galaxy, a magnetar begins drifting through space. Over thousands or millions of years, it slowly moves closer to our solar system. Eventually, this incredibly dense object, only about 20 kilometers wide, but more massive than our sun, enters our cosmic neighborhood. At first, humanity might not even notice. Unlike ordinary stars, magnetars are small and relatively dim in visible light. They do not shine brightly in the night sky the way normal stars do. Instead, they emit most of their energy in the form of X-rays and gamma rays, which are invisible to the human eye. Only specialized space telescopes are able to detect this radiation. But as the magnetar approaches closer to Earth, subtle signs would begin appearing. The first indications would likely appear in our technology. Satellites orbiting Earth are extremely sensitive to changes in radiation and electromagnetic fields. If a magnetar moved within several million kilometers of our planet, instruments aboard satellites might begin detecting unusual bursts of radiation coming from a previously unknown source. Astronomers studying the data might initially suspect a distant gamma burst or an unusual stellar object. But as they analyze the signals more carefully, a disturbing realization would emerge. The source of the radiation would not be distant at all. It would be approaching within days or weeks. Scientists across the world would confirm the existence of a magnetar. It's moving dangerously close to our solar system. At that moment, humanity would face a cosmic threat unlike anything ever experienced before, even at a distance greater than the orbit of the moon. The magnetar's magnetic field could begin interacting with Earth's own magnetic field. Subtle disturbances would ripple through our planet's magnetosphere. Satellites might experience unexpected glitches. Navigation systems could begin reporting small errors as the magnetar moved closer. These disturbances would grow stronger. Electrical systems on satellites could begin failing entirely. Communication networks that rely on satellite infrastructure would start breaking down. GPS systems used by airplanes, ships, and vehicles across the world might suddenly become unreliable or stop working altogether. On the surface of Earth, power grids could begin experiencing unusual fluctuations. Transformers and electrical equipment designed to operate within normal magnetic conditions might start overheating or shutting down. Modern civilization depends heavily on complex electronic systems. Everything from global banking networks to transportation systems relies on stable electricity and communication networks. As these systems began to fail, the world would quickly descend into confusion and uncertainty. But technological disruption would only be the beginning. The real danger would come from the Magnetars radiation. Magnetars occasionally release powerful bursts of gamma rays during events known as magnetar flares. These flares occur when the star's intense magnetic field rearranges itself, releasing enormous amounts of energy in the process. If such a flare occurred while the magnetar was relatively close to Earth, the consequences could be devastating. Gamma rays carry extremely high energy and can penetrate deep into Earth's atmosphere. When they interact with atmospheric molecules, they trigger chemical reactions that can break apart ozone molecules. The ozone layer acts as a protective shield that absorbs much of the harmful ultraviolet radiation coming from the sun. Without this protective layer, the surface of Earth would be exposed to far more intense radiation. Plants, which form the base of most ecosystems, are particularly sensitive to ultraviolet radiation. Large increases in UV exposure could damage plant DNA, reducing crop yields and harming natural ecosystems. Marine life in the upper layers of the ocean could also suffer significant damage. If the ozone layer were severely depleted by repeated magnetar flares, the long-term consequences for life on Earth could be profound. But even this might not be the worst-case scenario. If a magnetar came extremely close to Earth, perhaps within a few 100,000 kilometers, its magnetic field could become strong enough to directly interact with matter on our planet. Magnetic forces at that intensity could distort the shape of atoms and molecules. Materials that normally behave in stable ways might begin reacting unpredictably. Electronics would almost certainly be destroyed. The magnetic fields could induce enormous electrical currents in wires and circuits, burning out delicate components instantly. But the most disturbing possibility involves the effects on living organisms. Human bodies, like all living systems, rely on delicate chemical interactions between molecules. Proteins fold into specific shapes. DNA stores genetic information through complex molecular structures. If the magnetic field near Earth became strong enough to distort these structures, it could disrupt the biological processes that sustain life. Fortunately, such an extreme scenario is extraordinarily unlikely. Magnetars are extremely rare objects, and the chances of one wandering close enough to threaten Earth are incredibly small. Most known magnetars are located thousands of light years away, far beyond any realistic danger to our planet. Even so, studying these possibilities helps scientists understand how vulnerable planets might be to cosmic events. Throughout the history of the universe, many worlds may have experienced catastrophic radiation events from nearby stellar explosions or magnetar flares. In fact, some scientists have speculated that certain mysterious extinction events in Earth's distant past could have been influenced by bursts of cosmic radiation from distant astrophysical sources. While there is currently no evidence linking magnetars directly to any extinction event on Earth, the possibility highlights how interconnected our planet is with the broader universe. The cosmos is not isolated from our world. Events occurring thousands or even millions of light years away, can still influence the environment of our planet. And Magnetars represent one of the most powerful reminders of that connection. These tiny yet immensely powerful stars demonstrate how extreme the universe can become when gravity, nuclear forces, and magnetism combine in just the right way. They are objects capable of releasing enormous bursts of energy across the galaxy. And while Earth is safe from any known magnetar today, the existence of these objects reminds us that the universe is full of extraordinary forces beyond human control. Far out in the depths of space, magnetars spin silently in the darkness. From a distance, they may appear calm, almost peaceful, glowing faintly as small remnants of ancient stars. But beneath that quiet exterior lies one of the most violent environments in the universe. Unlike ordinary stars, magnetars possess a solid outer crust. This crust is not made of rock, like the crust of Earth. Instead, it is composed of an incredibly dense lattice of atomic nuclei, compressed together under extreme gravity. The pressure inside a neutron star is so intense that matter behaves in ways that scientists can barely recreate in laboratories. The crust of a neutron star is incredibly strong. In fact, scientists believe it may be the strongest material in the entire universe. The structure is held together by powerful nuclear forces and immense gravitational pressure. Under normal circumstances, this crust would be almost impossible to break. But magnetars are not normal. Neutron stars. The intense magnetic field surrounding a magnetar constantly twists and strains the star's crust. Imagine bending a thick piece of metal again and again. Eventually, even the strongest metal will crack under enough stress. The same thing happens on a magnetar. Over time, the magnetic field inside the star slowly shifts and rearranges itself. These changes place enormous pressure on the crust. The stress builds silently for years or even centuries. Then suddenly, the crust can no longer hold together. It cracks. This event is known as a starquake. The moment the crust breaks, an enormous amount of energy is released. The magnetic field surrounding the magnetar rapidly reconfigures itself, unleashing powerful waves of radiation into space. These bursts are called magnetar flares, and they are among the most powerful explosions known in the universe. To understand how intense these flares can be, imagine an event that releases more energy in a fraction of a second than our sun produces over thousands of years. That is the scale of energy involved in a magnetar starquake. When a starquake occurs, the magnetar emits a sudden burst of gamma rays and X-rays. These forms of radiation carry extremely high energy and travel across the galaxy at the speed of light. For a brief moment, the magnetar becomes one of the brightest sources of gamma radiation in the entire sky. Astronomers first began discovering these events in the late 20th century, when space-based observatories started detecting mysterious bursts of gamma radiation. At first, scientists were unsure what caused these signals. Some bursts appeared to come from distant galaxies. Others seemed to originate within our own galaxy. Eventually, researchers realized that some of these bursts were coming from magnetars. One of the most famous magnetar flares occurred on December 27, 2004. On that day, a magnetar located about 50,000 light-years away released an enormous burst of gamma radiation. The event lasted less than half a second. Yet during that brief moment, the magnetar released more energy than our sun produces in 100,000 years. Even from that enormous distance, the burst had measurable effects on Earth. Satellites orbiting our planet detected the sudden surge of gamma radiation almost immediately. The burst briefly affected Earth's upper atmosphere, causing a measurable change in the ionosphere. For a few seconds, The radiation from that distant star altered the electrical properties of Earth's atmosphere. That single event demonstrated just how powerful magnetars truly are. If the same flare had occurred much closer to Earth, the consequences could have been catastrophic. Astronomers classify magnetar flares into several different categories. The smallest events are known as short bursts. These flares release relatively small amounts of energy and last only a fraction of a second. Larger events are called intermediate flares. These may last several seconds and release far more energy. But the most dramatic events are known as giant flares. Giant flares are incredibly rare, but when they occur, they release enormous amounts of radiation in an extremely short time. The 2004 event was classified as one of these giant flares. During such an event, the magnetar's magnetic field suddenly rearranges itself in a massive release of energy. The radiation produced by this process spreads outward through space in all directions. Any planet or star system located nearby would be bombarded with intense gamma radiation. Fortunately, giant magnetar flares are rare, even among magnetars. Scientists believe they may occur only a few times. But when they do occur, they can be detected across vast distances in space. These flares also provide astronomers with valuable clues about the internal structure of neutron stars. By studying the radiation produced during starquakes, scientists can learn about the strength of the magnetar's crust and the behavior of its magnetic field. In some ways, starquakes on magnetars are similar to earthquakes on Earth. When tectonic plates shift beneath Earth's surface, they release energy that travels through the planet as seismic waves. These waves allow scientists to study the internal structure of Earth. Similarly, when a magnetar's crest cracks, the resulting vibrations travel through the star itself. These vibrations can affect the radiation emitted by the magnetar, allowing astronomers to study the interior of the star. Some observations have even detected oscillations in magnetar flares that appeared to be caused by vibrations traveling through the star's crust. These observations provide rare glimpses into one of the most extreme environments in the universe, magnetar. Starquakes remind us that even the most powerful objects in the universe are not completely stable. Despite their immense gravity and incredible density, magnetars remain dynamic objects constantly evolving and changing. Their magnetic fields twist and shift over time. Their crusts strain under enormous pressure. And occasionally, the stress becomes too great when that happens. The crust cracks with a violence unlike anything we experience on Earth. A burst of energy spreads outward across the galaxy. Silent signal from one of the universe's most powerful stars. And somewhere, thousands of light years away, astronomers detect the brief flash of radiation and realize that another magnetar has unleashed its incredible power. But magnetar flares may not only produce gamma radiation. Some scientists believe these events may also be connected to one of the most mysterious cosmic signals ever discovered. For decades, astronomers believed they had a fairly good understanding of how stars behave. They knew how stars formed from collapsing clouds of gas, how they spent most of their lives fusing hydrogen into helium, and how the most massive stars ended their lives in violent supernova explosions. Yet the universe has a habit of surprising scientists with new mysteries. And one of the most puzzling discoveries in modern astronomy appeared only recently, in 2007. Astronomers analyzing old data from a radio telescope in Australia noticed something strange. Hidden within the data was a sudden flash of radio waves that lasted only a few milliseconds. The signal was incredibly powerful, yet it appeared only once and then vanished. At first, researchers were unsure whether the signal was even real. It might have been interference from Earth-based electronics or a glitch in the telescope's instruments. But as scientists continued studying data from other telescopes around the world, they began discovering more of these strange signals. Each one shared the same mysterious properties. They were extremely brief. Lasting only a few thousandths of a second, they were incredibly powerful, releasing enormous amounts of energy. And they appeared to originate from very distant regions of space, often billions of light years away. These mysterious signals became known as fast radio bursts, often abbreviated as FRBS. At first, the discovery created intense excitement and confusion within the scientific community. Because the bursts were so brief and unpredictable, they were extremely difficult to study. By the time astronomers detected one of these signals, it had already disappeared. Yet the amount of energy contained in each burst was astonishing. In just a few milliseconds, a fast radio burst could release as much energy as the sun produces in several days. The question that puzzled scientists was simple, but profound. What could possibly create such an enormous burst of energy in such a short amount of time? Over the years, many different theories were proposed. Some scientists suggested that fast radio bursts might be produced when neutron stars collide with each other. Others proposed that the bursts might come from black holes, interacting with nearby matter. A few more speculative theories even suggested that fast radio bursts might be artificial signals created by advanced extraterrestrial civilizations. While the idea of alien technology captured the imagination of the public, most astronomers believed a natural explanation was far more likely. But identifying that explanation proved difficult. The main challenge was that fast radio bursts happen extremely quickly. Most radio telescopes observe only a small portion of the sky at any given time. When a burst occurs, it may last only a few milliseconds before disappearing forever. Catching one in the act requires both luck and sophisticated instruments capable of recording enormous amounts of data. As technology improved, astronomers began building new radio observatories designed specifically to detect fast radio bursts. One of the most important of these facilities is the Canadian Hydrogen Intensity Mapping Experiment, commonly known as CHIME. CHIME is a large radio telescope located in British Columbia, Canada. Unlike traditional telescopes that point toward specific targets, CHIME constantly scans a large portion of the sky. This design makes it extremely effective at detecting short-lived signals like fast radio bursts. Within a short time after becoming operational, CHIME began discovering hundreds of new fast radio bursts. Some of these bursts appeared only once and were never seen again. Others behaved differently. These repeating bursts came from the same location in space and occurred multiple times over months or years. The discovery of repeating fast radio bursts provided a crucial clue. If the bursts were produced by catastrophic events like neutron star collisions, they would likely occur only once. But repeating bursts suggested that whatever was producing them could survive the process. This observation pointed scientists toward magnetars. Magnetars are known for releasing enormous bursts of energy during starquakes and magnetic reconnection events. These bursts can produce powerful emissions across many parts of the electromagnetic spectrum, including X-rays, gamma rays, and radio waves. In 2020, astronomers finally observed a breakthrough event. A magnetar located within our own galaxy released a burst of radio waves that closely resembled a fast radio burst. For the first time, scientists detected a fast radio burst originating from a known magnap, provided strong evidence that at least some fast radio bursts are produced by Magnetars. Experiences. A starquake, or a sudden rearrangement of its magnetic field. Enormous amounts of energy are released. Under certain conditions, this energy can produce a powerful pulse of radio waves that travels outward through space. As the pulse moves through interstellar gas and dust, it spreads across vast distances. By the time it reaches Earth, it appears as a tiny but detectable flash in radio telescopes. Although the signal lasts only a few milliseconds, it may have traveled for billions of years before reaching our planet. In other words, when astronomers detect a fast radio burst, they are witnessing an event that may have occurred long before life even existed on Earth. These bursts act like cosmic messages sent across the universe, carrying information about the extreme environments where they were created, studying. Fast radio bursts has also given scientists a new tool for exploring the structure of the universe as radio waves travel through space. They pass through clouds of gas and plasma that slightly alter the signal. By analyzing these changes, astronomers can learn about the distribution of matter between galaxies. In this way, fast radio bursts help scientists map the otherwise invisible material that fills intergalactic space. Magnetars, once considered rare and mysterious stellar remnants, may therefore play an important role in helping astronomers understand the large-scale structure of the universe. Each burst they produce becomes a tiny probe, traveling across billions of light years. A brief flash of radio waves that carries information about distant galaxies, intergalactic gas, and the nature of extreme astrophysical objects. Yet despite these discoveries, many mysteries remain. Not all fast radio bursts appear to come from magnetars. Some signals show properties that scientists do not yet fully understand. It is possible that multiple different astrophysical phenomena produce these bursts. The universe may still hold many secrets waiting to be discovered. But one thing is, certain magnetars are among the most powerful engines in the cosmos. They twist space with their magnetic fields, crack their own crusts in violent starquakes, and send powerful signals across unimaginable distances. And somewhere in the darkness between the stars, magnetars continue spinning silently, occasionally releasing brief flashes of energy that travel across the universe. Tiny signals that remind us how mysterious and extraordinary the cosmos truly is. Magnetars may be among the most powerful objects in the universe, but like all cosmic phenomena, they do not last forever. Despite their incredible magnetic fields and violent bursts of radiation, magnetars are actually relatively short-lived compared with many other astronomical objects. In cosmic terms, their most active phase is surprisingly brief. To understand why magnetars eventually fade, we must look again at the source of their incredible power, their magnetic fields. The magnetic field of a magnetar is not a static structure that remains unchanged forever. Instead, it is a dynamic and evolving system of energy stored around and within the star. Over time, the magnetic field gradually loses energy as it interacts with the star's crust and surrounding space. Each burst of radiation, each starquake, and each flare releases a portion of that stored energy into the universe. Slowly, almost imperceptibly, the magnetar begins to weaken. In the earliest stages of its life, a magnetar is extremely active. Its magnetic field is twisted and unstable, and the star may experience frequent starquakes as the crust struggles to adjust to the immense forces pulling and twisting it. During this time, magnetars can release powerful bursts of X-rays and gamma rays that are detectable across vast distances in space. Astronomers believe that the most active phase of a magnetar may last only around 10,000 years. That might sound like a long time by human standards, but on astronomical timescales it is incredibly short. Many stars shine for billions of years, Yet magnetars unleash their most dramatic activity in a tiny fraction of that time. As the centuries pass, the magnetar's magnetic field gradually untwists and relaxes. The enormous stresses inside the star begin to decrease. Starquakes become less frequent, and the bursts of radiation grow weaker. Eventually, the magnetar settles into a quieter state. At this stage, it begins to resemble an ordinary neutron star. The magnetic field is still strong compared with most astrophysical objects, but it is no longer powerful enough to dominate the star's behavior. The dramatic flares and bursts that once defined the magnetar become rare or disappear entirely. What remains is a dense, slowly spinning neutron star drifting through space. But even in this quieter phase, neutron stars remain extraordinary objects. Their density remains extreme, their gravity remains immense, and their rotation can still produce beams of radiation that sweep across the cosmos like cosmic lighthouses. Some of these neutron stars become pulsars, emitting regular pulses of radio waves that astronomers can detect from Earth. Others slowly cool and fade into near invisibility, becoming faint stellar remnants that wander silently through the galaxy. The long-term fate of magnetars is still an area of active scientific research. Some scientists believe that as the magnetic field weakens, the magnetar gradually transitions into a typical neutron star. Others suggest that certain magnetars may retain strong magnetic fields for longer periods, continuing to produce occasional bursts of radiation. Even as they age, there is also another fascinating possibility. Some theories suggest that under certain conditions, magnetars could eventually collapse into black holes. This would require additional mass to accumulate onto the magnetar, perhaps from a nearby companion star or from surrounding gas in space. If enough material fell onto the magnetar, the added gravity could push the star beyond the maximum mass that neutron star matter can support. When that limit is exceeded, gravity would take over completely. The neutron star would collapse further, compressing matter beyond the neutron state and forming a black hole. In that moment, the magnetar would disappear from the universe as an observable object, replaced by a region of space where gravity is so intense that not even light can escape. While such transformations are rare, they demonstrate the remarkable variety of paths that stellar remnants can follow after the death of massive stars. Magnetars also leave lasting marks on the space around them. The supernova explosion that created the magnetar would have ejected enormous clouds of gas and dust into space. These expanding clouds form beautiful structures known as supernova remnants. Over thousands of years, these remnants spread across vast regions of space, enriching the surrounding interstellar medium with heavy elements. These elements eventually become part of new stars, new planets, and potentially even new forms of life. In this way, the death of one star helps create the raw materials for future generations of stars and worlds. Magnetars therefore represent both destruction and creation. They are born from the violent death of massive stars, yet the explosions that create them help shape the evolution of galaxies. Their powerful radiation illuminates the distant universe, allowing astronomers to study extreme physical processes that cannot be reproduced on Earth. And their mysterious signals, such as fast radio bursts, may help scientists map the structure of the cosmos itself. Even though magnetars are rare, their impact on astrophysics has been enormous. They challenge our understanding of how matter behaves under extreme pressure. They push the limits of magnetic physics. They reveal new forms of radiation and cosmic phenomena that were once completely unknown. Perhaps most importantly, Magnetars remind us that the universe is far stranger and more powerful than our everyday experiences suggest. On Earth, we live in a relatively gentle environment. The forces we encounter in daily life, gravity, magnetism, temperature are mild compared to the extremes found in deep space. But beyond our planet, the universe contains objects capable of bending light, crushing matter into unimaginable densities, and releasing energy on scales that dwarf entire civilizations. Magnetars are one of the clearest examples of this cosmic extremity, tiny compared with most stars, yet more powerful in magnetism than anything else known in existence. Silent most of the time, yet capable of unleashing bursts of energy that travel across galaxies. They are reminders that the universe is filled with wonders still waiting to be explored. And even as magnetars slowly fade and transform into quieter remnants, their legacy continues. The energy they release spreads across space. The elements forged in the stars that created then become part of new cosmic structures. And the signals they send across the universe continue to reach distant observers, telling the story of some of the most extraordinary objects ever discovered. The universe is vast beyond imagination. Within it exist objects so powerful that they challenge the limits of physics itself. Among those objects are Magnetars, tiny remnants of dead stars whose magnetic fields are strong enough to distort atoms, bend light, and unleash bursts of energy that travel across entire galaxies. These extraordinary stars are born in the violent deaths of massive suns, forged in the heart of supernova explosions where gravity crushes matter into one of the densest forms. Known to science for thousands of years, magnetars spin silently through space, their powerful magnetic fields twisting and shifting as enormous forces build inside their crusts. Occasionally, that pressure becomes too great, the crust cracks, a starquake erupts, and for a brief moment, the magnetar releases an explosion of energy, so powerful it can be detected across the universe. Yet even these incredible objects cannot last forever over time. Their magnetic fields weaken, their violent eruptions fade, and the magnetar slowly becomes just another neutron star drifting through the galaxy. But during their brief and dramatic lifetimes, magnetars reveal something profound about the universe we live in. They show us that the cosmos is not a quiet place. It is a dynamic and evolving system filled with extreme forces, mysterious phenomena, and extraordinary objects that push the limits of what we understand about nature. And somewhere out there, in the dark depths of our galaxy, magnetars continue to spin silently waiting for the next moment, when their immense magnetic power will crack the surface of a dead star and send another signal racing across the universe. A reminder that even in the vast emptiness of space, incredible forces are always at work.